e raised to the negative x squared. This is a classic problem because it can't be done by hand. Oops. So that integral right there cannot be done by hand. Like there's no closed form of it. So when I go ask, it gives me the error function, right? So it's just like, can't really do it. But if you scroll down, it will give you the answer in its series, as a power series, it gives you the answer. So this, if you were like really needing to get an answer for it, you could use this, and then you could actually go further out. I can ask it for more. Can I ask it for more? I can't ask it for more? Oh man, it won't give me more digits on that?
Is it the big O notation?
No. No, that's just defining what it is, like if you don't know what big O is. Yeah, I can't ask for more. I probably have to pay for that. I can do it on my program, but I don't have time. So imagine this keeps going forever. And so you could use that. That's the antiderivative. Yes?
How do you know your margin of error if you technically don't?
There's ways to find the margin of error. You can figure out how far you need to go out. There's formulas for it, like tells you go out 10 places, or 10, go out 100, go out 1,000. All right, so this is pretty good, right? This is pretty powerful. I really want to drill this in. Every function has a power series, every one of them, right? That has a power series. Now, I'm getting ahead of myself, but I want to just show you, again, the implications of this. I'm going to write down the power series for this right now. It is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5 over 5 factorial plus x to the 6th over 6 factorial plus ... Now, you're taking that on faith, right? I'm telling you that. You're believing me, right? I can show you, hopefully next week, how to create that yourself. Like I will show you how to create this series from e to the x. But if you take that on faith that that is the power series for that, it goes on forever, then what should the derivative of that be? What's the derivative of e to the x? It should be itself, right? Let's try. Take derivative of this. So start taking derivative of this. What's derivative of 1? Okay, what's the derivative of x? 1. Okay, now here, this power rule, 2 comes out. What's 2 factorial? 2 times 1, right? So the 2's cancel and you just get x. Okay, here, the 3 comes out. 3 factorial is 3 times 2 times 1, isn't it? Yeah. So the 3's cancel. You get x squared over 2 factorial. And then here, this is really 4 times 3 times 2 times 1, right? So when you do the power rule, 4 comes out, cancels. You get x cubed on top, and what's left on the bottom? 3 factorial. And then you keep going, right? X to the 4th, 5 comes out, cancels 1, and you get 4 factorial. And guess what? What is that? That's the same thing.
Oh, yeah.
It's the same exact series. Exactly the same. This is the only function that does that. It's the only one. There's no other function, there's no other power series that when you take its derivative you get the same power series you started with, except that one. Right? What if you wanted to integrate it? What's the antiderivative of e to the x? Yeah, it's e to the x plus c, right? So let's start taking antiderivative. What's the antiderivative of that? X, okay. What's the antiderivative of that? 1/2 x squared, right? What's the antiderivative of that? Well, you'll get an x cubed right on top, and then you'll have to put a 1/3 in front, and then that 3 in front hits the 2 factorial and becomes a 3 factorial. So you get 1 over 3 factorial x cubed. Do you see how this is exactly the same thing? Right? Now I'm missing the 1 out front, right? But what do I have every time I do an antiderivative? Plus c at the end, right? So that's my constant. The 1 is like my constant. Anyways, every function has a power series. Sine does, cosine, all of them. And so what we're doing now is we're kind of getting comfortable with the idea of a power series. Let me back this up so it doesn't slow my computer down. All right. Now we need a more general definition. I mean, it's kind of good news and bad news. So Yes.
Natural log have one too?
Yes, natural log has one as well. Yep. I won't derive it right now because time, but we can do it. We'll do it later. So the power series I just gave you, right? This right here. I'm going to make a small change to it because you know how I did that picture and it started to like do its thing and started to like mold itself onto the function, but it only worked between 1 and -1? And you're like, well, what's the use of that if I really am more interested in like being somewhere else? I don't like being stuck between 1 and -1, right? That kind of limits my ability to approximate something. So what if you want to move it? Well, how do we move functions in college algebra? How do you shift horizontally?
It's like x plus 3.
Inside with the x, you subtract a number to move it to the right, right? And you add a number to move it to the left. What I want to do is I want to rewrite that power series that I just wrote up there on the board for you, but I want to be able to shift it. So instead of doing x to the n here, we're going to replace the x to the n with x minus a to the n. And what that will allow me to do is make any sort of horizontal shift I want of the power series. And this is the most general form of the power series right here. So y'all see? Before that formula over there, I really was saying a was 0. And then it was just x to the n, right? But now I'm saying, let's say we can subtract a number. If we do that, then this is called a power series about a, or a power series centered at a, or a power series in x minus a. All right? That's the language we use to describe that power series. So all that changes is that instead of x, we have x minus a, right? Just raised to higher and higher powers. I want you to notice 3 things about this. First, that first term, when you do n is 0, x minus a to the n, we are going to say that that's equal to 1. Y'all buy that? This x minus a to the 0 power is 1. The next thing, if I replace x with a, if I say, hey, plug a in for x, what happens to all the terms? What happens? That goes to 0, that goes to 0. Everything goes to 0, right? Except for the first one. Okay, that's why I'm saying you have to, these 3 things in order. We are defining this to be 1. We are defining it that way. Okay, that is 1 because it's raised to the 0 power. For all the other terms, if I replace x with a, that's 0, gone, 0, gone, 0, gone. Everything else goes away. So what would be left if I plugged in a for x? 1n times c sub 0. So you would get your first constant. So if x is a, then everything goes away, right? You get 0. I didn't put it there. But it would converge, wouldn't it?
Yeah.
I mean, like if I told you, hey, plug in a, the only thing you'd be left with is this, right? And it's just a number, and that's converging to that number. So that's what this is. If x equals a, the series converges. So for all power series centered at a, if x equals a, it's a convergent power series. For all power series centered at a, if x equals a, then the series converges. Which means for any power series, I can make it converge at least 1 value. Right? Give me any power series. I don't care what it is. I don't care what the power series is. Right? If we define this power series centered at a, if we define this to be a function, f of x, then I guarantee there's at least 1 value I can plug into this to get an answer. And it's what? What value do I have to plug into this to get an answer?
Whatever a is. Yeah.
A, right? Whatever a is. If I plug in a, boom, I get an answer. It converges to that. So I have at least 1 point of convergence for every power series.
Oh.
Let's do an example. Yes?
If all functions can be power series, does that mean that?
Almost all. Almost all. There are examples you can come up with. We need differentiability of the function. We need to be able to take nth order derivatives, so you have to be able to take derivatives repeatedly in order to define a power series, which most functions that we deal with in the real world, yes, but mathematicians, of course, have found some that won't work, right? So I can't say all, but a huge category of them do. Yeah. Okay. Good? All right. Example 1. F of x, I'm defining a function, right? I'm defining it to be this power series right here. This is not the geometric series that we just looked at. This is a new one, right? There's a new power series. I want to know, first of all, what's A? So where's this thing centered? Then I want to know what is the formula for C sub n? And then I want to know what is the domain of F. In other words, what values of x do I plug in here that make that converge? A is 0, right? So how do you know A is 0? That's right. There's nothing attached to the x that's being raised to the n power, right? In fact, you could, if you want, look at this as being x minus 0 to the n, right? And so the A is 0. What's the formula for C sub n? So what is the formula that's cranking out the coefficients? N factorial, right? It's the thing sitting in front, right? N factorial. That's your C sub n formula. And finally, what is the domain, right? What values of x, I'll get it, what values of x will make this converge? That's right. What values of x? Now that's not something you're going to be able to look at and tell me, okay? You're not going to. So let me show you how we're going to do it. I have a series, right? And I want to know when it converges, right? When does it converge? For what values of x? So I have an x in there that I have to pay attention to. And then I have this list of tests to do, right? And there was one test that I called the almighty test, and it was the ratio test, right? I'm going to run the ratio test on that series right now. And hopefully from that I can conclude that it converges somewhere. So ratio test. So I want to take the limit as n goes to infinity of the absolute value. And then the way the ratio test works is that you're going to do a ratio, right? The first part, the top of the ratio, is this formula, everything here, with what plugged in for n? N plus 1. So I'm going to plug in n plus 1 factorial x to the n plus 1. That's a sub n plus 1. Then divide that by a sub n, which is that formula just the way it appears up here. And what do I want this to be? I want this limit to be what? Less than 1, right, for convergence? So I'm asking myself, when is this less than 1?
And that less than 1 for convergence is based on the ratio.
That's the ratio test, yes. It says we have to have less than 1. If it's equal to 1, the test fails. That's important. If it's equal to 1, the test fails. If it's greater than 1, it's divergent, okay? So let's now do that. I don't need that. Okay, so now let me clean this up. This is limit, n goes to infinity, absolute value. Okay, the n plus 1 factorial I'm going to write is n plus 1 times n factorial. That's a property of factorials we talked about way back when we first started talking about factorials, that you can peel the first one off. Then the x to the n plus 1 I'm going to write as x to the n times x. And then on the bottom, n factorial, and then x to the n. I want that to be less than 1, right? Are y'all following what I'm doing here? This is just properties of factorial, and then x to the n plus 1 can be split into 2 pieces. That allows me to cancel some stuff, right? So this allows me to cancel this, and this, and this, and this. Whoa, okay, cool. That's good. Limit n goes to infinity, absolute value, n plus 1, and then x, right? And I need that to be less than 1. So remember, what we're saying is that I'm going to take a value of x, right? I want to know if I take a value of x and I plug it in right here, will it converge or not? So I'm trying to figure out for what values of x does that happen for. So the number I plug in has to be a number. It can't be infinity, Okay, infinity is not a number. So I have to plug in like 5 or 6 or 7. So imagine that I've plugged a number in, right? I plugged in x, and here's where I've gotten. I need this to be less than 1. What happens when n goes to infinity here? This goes to infinity, right? Is that going to be less than 1? No, right? Unless x is what?
0.
X is 0, right? But what did we say a was? 0. Didn't we say all series will converge when x is a?
Yeah.
So this will converge if x is 0, right? But otherwise it will diverge, right? Because this is going to go to infinity times x. If I take that absolute value, that's not going to stay less than 1. See, because x is fixed. X is a fixed number. You can't tell me x is going to infinity or anything like that. X has to be a fixed real number. So if I take a fixed real number and I multiply times in something that's getting infinitely big, there's no way that that stays less than 1, right? This will not be true if x is not 0, right? If x is not 0, this is not true. So that means, let's draw our conclusion. What's the domain of this function? For what values of x does it converge? 0, that's it.
Yeah.
Otherwise, it diverges. So the domain of this is just, let's just say x is 0.
Yeah.
That's it. It's a boring function. It is a function that is only defined at one point, and that's 0. That's it. Boring. First example is just to show you what we're going to do. All right? Go ahead.
Can you still say that this function has an a, even though the a is
Yeah,
0?
a is 0. Yep. All right, let me get to our next example. Same questions, different series, different power series. I just gave you an example of a power series that converges at a single point, right? A pretty useless power series, if you ask me, because who wants to deal with a function that's only defined at one point, right? I mean, what's the use of something like that, right?
So does that really help you at all for any? Because as you said, you know that it's going to be defined at least one point. That's not really the point.
What this is leading to us, or what this is leading to, is that when it comes to power series, when you talk about convergence, there's only 3 possibilities. It converges at a point, an interval, or everywhere. And I'm going to give you an example of each one. And then I'm going to give you a theorem that says those are the only 3 possibilities. So here's your next example. What's a here? 3. Not negative 3, positive 3, right? If that was a plus 3, then I would say negative 3. So a here is 3. So I know for sure this converges at 3, right? If I plug 3 into that, we've got convergence. But the question is, does it converge anywhere else, right? So now, what's the formula? What is our formula for C sub n? Be careful here. Just 1 over n, right? 1 over n. So when you look for the formula for C sub n, you ignore that part up here. The part that has the x being raised to the power, that part you ignore, and you look at the rest of everything, and that's your C sub n, which is 1 over n here. All right, find the domain. Ratio test. Limit, n goes to infinity. Absolute value. Okay, I'm going to replace all my n's with n plus 1. And then divide that by replacing nothing, just leaving it just the way it appears. And I want that to be less than 1, right? But that becomes limit, n goes to infinity, absolute value. Okay, we have x minus 3 to the n times x minus 3 all over n plus 1 times, I'm flipping the one on the bottom up to the top, flipping things over. I think we've done that enough times, yeah? Taking this fraction, flipping it, and then also splitting the x minus 3 to the n plus 1 into 2 pieces. Any questions on what I've done algebraically there? Sure?
You have to keep the less than 1 on there?
Yes.
Always keep it.
Because we're checking to see what the domain is. We want to know when it converges, and it only converges if this is less than 1, right? So this is more of a check. We're asking ourselves, when is this true, right? Gone? Now, at this point, the standard rule of thumb for me when I do these problems is that I want to know what's happening to the piece with n in it, right? And the part with x in it is kind of a separate thing. So I like to split this up into two different ideas. I have limit n goes to infinity, absolute value. I have n over n plus 1 times x minus 3, absolute value less than 1. So I'm kind of like putting the n stuff together, and then I bring the stuff with x's and I separate it out kind of into two different factors. I already know that if I let x be 3, this is 0, and that's definitely less than 1. But the question is there any other values of x that would make it less than 1? Take your limit, let n go to infinity. What do you get this time? L'Hopital, you get 1, right? This goes to 1, right? This goes to 1. That doesn't go to infinity, right? So when I apply the limit now, so no more limit, I'm going to apply the limit. That turns into a 1. So don't I just get the absolute value of x minus 3 must be less than 1? Right, because that goes to 1, sorry, not 0, goes to 1. You take the limit, that goes to 1, and so all that's left is the absolute value of what's in here. And I need that to be less than 1, right?
So,
hold on. Okay, so I've got that absolute value inequality over there. What we need to do is we all need to know how to solve that, and I know some of you don't, it's okay. I'm going to show you real quick how to solve this absolute value inequality. Whenever you have an absolute value inequality like this, I have the absolute value by itself, right? Less than or greater than, doesn't matter what's here, 1. Well, actually less than, let's stick with less than. Less than 1. What you do is this. You drop the absolute value, and you keep it exactly the same, but you have to then go on this side and put greater than the opposite of that number, -1. To say that the absolute value of x minus 3 is less than 1 means that that x minus 3 must live between -1 and 1. The distance from a number to 3 has to be less than 1, means that this has to be smaller than 1 or greater than -1. That's just the standard procedure. And now, let's get x by itself. Let's add 3 to everything. And you get 2 less than x less than 4. Okay, now your question. No?
I was wrong.
Okay. Yes?
I know it's an old question, but to do the L'Hopitals on that, do you have to split it into two limits? And I know
Well, this isn't going anywhere. N's not in here.
So we can split it because it's x?
Yeah, because it's x, we can ignore it. Because the only thing that's being impacted is the n, right? The n's going to infinity, which has no impact on this, so I can ignore it. If that goes to 1, which it does, right, then now I can say, okay, that goes to 1. 1 times that is this.
Okay.
Yep. All right. Are we understanding so far? What we've concluded thus far is this. For this series to converge, right? For this to converge, I need a to be 3, and I could also have x be between 2 and 4, but isn't 3 in here? 3 is right in the middle, isn't it? It always turns out that way, that a will be in the middle. That's why they say it's centered at a. Okay, but so this so far answers the question. This is like my domain of that function. But we have one thing we haven't really addressed, and that is the fact that the ratio test fails when? When it equals 1, right? So what I need to do now is say, what would happen if that limit here turned out to equal 1, right? What would make this 1? What would make this equal 1? What number would I plug in here to make this equal 1? 4. What else would work? 2, right? 4 minus 3 absolute value is 1. Or 2 minus 3 absolute value is also 1. So do you see these two endpoints that right now I'm not including? I actually need to see what happens at those endpoints. I need to see at 2, do I get convergence or not? Because I know ratio test fails, right? And at 4, I know that if I try x is 4, the ratio test would fail as well. Yes?
So in like a color problem, if we get it like that, where it's a double inequality,
Yep.
do you want to plug in endpoints in?
Yes, we have to check the endpoints now. All right? So far, here's where we are. Let's now check the endpoints. Do y'all understand that the reason we're checking the endpoints is because when you try and plug in the endpoints 4 or 2, if you try the ratio test, you get 1, and the ratio test is inconclusive when you have 1. Yes? Okay, so now checking endpoints. Test or check endpoints. Endpoints. I can't spell, can't write endpoints. All right, let's start with the left endpoint, x is equal to 2. I want to know what happens to that series when x is 2, right? Now, I don't want to run a ratio test because I know what would happen, right? The ratio test would give me 1, and then I would have a failed test, right? So why don't I just do this? Let me rewrite what's up there, and let me replace x with 2. And that would become sum n equals 1 to infinity of, what, negative 1 to the n over n? Isn't that what it would turn into? See, we're not looking at a power series anymore, are we? No. We're looking at an actual series from the previous sections. Because x isn't there anymore because we replaced x with 2, or negative 2, right? So now we're back and we have that list of tests. What tests would you like to run on this? Can't do comparison because to do a comparison you have to compare, this has to be positive only, right? Comparison requires that the terms are positive only. So can't do comparison. Alternating series test. Why? Because it alternates, right? I mean, so that's what we want to use. So how does the alternating series test go? Alternating series test. What do? There's two things I have to show. First, I have to show, well, with alternating series, I have to rewrite this as negative 1 to the n times 1 over n, like split it into two pieces, and I'm focusing all of my attention on that piece right there. So I have to show that it's what? Decreasing, and then the second condition? See if that sequence goes to 0. If those two things are true, it's convergent. So first thing is 1 over n decreasing. Right, that's the first thing. Is it decreasing? That means when I plug in n, is that bigger than when I plug in n plus 1? Look, we've done this before. This was last week, so I can't spend too much time running alternating series test again, going through all the details. But I'm running the test, cross multiply, whatever, I get n plus 1 is greater than n, and that's true. So it is decreasing. The second condition is I have to take the limit as n goes to infinity of this 1 over n, and I need to check that it goes to 0. And it does. That goes to 0, right? And what does that mean? What's our conclusion? It's convergent. Therefore, it converges. Which means over here, remember we said it converges between 2 and 4? I just determined that it converges at 2, right? So I'm going to change that to that now, because I can include the 2. You see? These are one of my favorite problems to put on a test because you have to do a lot of different things and bring it all together, right? I'm not done. I have to do the other endpoint, right?
So I'm guessing right now we can't assume that just because one.
You can't assume.
Yeah.
Yeah, and on test I like to make it where it does one thing at one endpoint and something else at the other endpoint. Because that really shows your understanding and your, yeah, just you got like a big picture of what's going on here. Now I'm testing x is 4. So go to your series, power series, replace x with 4. Okay, if we do 4 minus 3, we get 1 this time, right? What's 1 to any power? 1. So this is 1 over n, and that's what type of series? Harmonic, and it diverges. And therefore, you do not want to include the right endpoint. And so your interval, right, the answer, if you wrote it as an interval, right, what is the domain of this function? It would be this interval, 2 to 4. Bracket, include the 2. Parenthesis, don't include the 4.
Should we write it like that?
Yep. I mean, I'm okay with you writing it this way as well. But
Okay.
most textbooks will just go to interval notation. Okay, so that means that this power series converges on this interval So if I had the computer try and draw this power series, between 2 and 4, I should get a picture of something, which I think I have it do here. Yeah, I do. Let me zoom this out.
What happens to the n in the exponent as it turns to 1 over n for the fourth one?
Right here?
Yeah.
This is 1, right?
Right.
What's 1 to any power? Right? Now, if it was -1, that would be a problem because it would alternate. But because it's +1, it's just 1. OK, so this is it right here. This is the actual series. Ignore the red, OK? I'm cheating, OK? The red one is what this function converges to. Remember earlier I put 1 over 1 minus x and I graphed that in red and then I made the black one converge to it? This red one, I'm not telling you where it comes from. All right? So you just have to believe this is what it's going to converge to. There's the series right there, and now I'm going to start throwing terms in here. Boom, 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 boom. The more I do, right, I'm leaving the dotted traces behind to show you like where I came from and what I'm turning into. And you can see that I'm turning into the red one the further out I go. And this is only happening between 2 and 4. If you go outside of 2, it does something different, right? Well, actually, it looks like it's doing pretty good over there. But over here it does too. Yeah, you get the idea. All right, another one? Ooh. All right, this is a pretty famous function. See, there are some functions that you know, I told you that e to the x has a power series, right? Pretty much every function you've ever learned has a power series. But there are other functions that are just power series that we don't have a function for. You know, like, it's like an unnamed, well, this one has a name, but there's, like e to the x has a power series. So when you look at that power series, you say, oh, that's e to the x. There are some power series that when we look at them, we don't have something that we call, like, we don't, oh, that's sine x, or that's, this is an example of one of those. It's only defined as its power series. And it's called the Bessel function of order 0. And the Bessel function of order 0 has to do with harmonics and vibration of membranes. If you get like a drum and you hit it, and the vibration is modeled by these Bessel functions. We'll look if we can in a second. Let's just first answer the question. All right, how does that series look to you? J, they use J, okay, I don't know, Bessel, J, don't ask me. Capital J, subscript 0 because it's order 0. There's a J sub 1 Bessel function, a J sub 2, right? There's different order Bessel functions. The J sub 0 Bessel function is that power series. All right, what's A? 0 again, right? Do y'all see that I don't have like x minus a number there?